Good morning, everyone. I'm here in Marseille in my office. Sorry that I cannot be with you in person. I was asked to speak about the use of atlases in the context of personalized brain modeling. And actually, this is a very important topic because when we want, with the ambition of building personalized high-resolution brain models, there are actually two elements that are extremely important. What we're interested in is using brain models for clinical applications. That means, you mentioned epilepsy, we are using it nowadays also for Parkinson's disease, for biomarker development in applications for Alzheimer or generally neurodegenerative diseases, including multiple sclerosis. Parkinson's is a neurodegenerative disease, and dementia in general, but also for healthy aging. Yeah, so it is useful. And what we need in this context are actually, number one, we need to be able to make patient or subject specific statements. Without personalization, there is no translation into the clinic. Yeah? This is very important to understand. And in order to bias our parameters in the brain models, we need to use non-invasive, preferably non-invasive brain imaging data of the individual. Those are typically they are always in vivo data, yeah, but those are typically not on a very high resolution level available. Example, MRI data, structural MRI data. So that needs to be improved by using ex vivo data at very high resolution, because that is the other element that makes that has been demonstrated previously, namely the fact that the use of high resolution data improves the predictive power, outperforming actually the use of low resolution individual data. There is inter-individual variability we deal with. This is a justification for personalization, but high resolution outperforms that. So we need to get these two elements together. That is personalization and high resolution, or said differently, in vivo and ex vivo data, to put them together in the same reference framework, in order to connect it with the existing simulators that we have in EBRAINS. You were talking about brain atlases, different brain atlases that are available in EBRAINS. We have also different simulators available in EBRAINS, each of them being dedicated to a particular level of description. Like the Virtual Brain is the one that we are using for full brain network simulation studies. So this needs to be merged together in order essentially to enable the knowledge that we are generating, accumulating in the atlases, to inform the models, to perform better simulations in order to translate the knowledge that is being generated through this into the clinics. And this is essentially the process I want to walk you through, actually step by step. And you have talked about the big brain and the atlas that is linked to this, the big brain histological space. Here you see a representation thereof. Underneath you see Roxana Koymans, who is actually working with one of the brains that are being used to currently being scanned in different institutions in Europe, primarily in Jülich, in Paris and in Amsterdam, in which actually individual tranches are being represented to obtain a very high resolution on the 20 micrometer level. On the right-hand side, you'll see representations from the previous brains that have been made. So here use immunohistological staining, and on the right-hand side you see an example from polarized light imaging representing individual fiber orientations. Key to this effort is actually to have an atlas providing us with a shared reference space that allows us to obtain data from heterogeneous sources via spatial nonlinear transformations, mapping them from these sources in the different spaces, for instance, like here in the MNI space, yeah, and mapping them in the shared brain reference space in order to make them mutually available. Connectivity plays a very important role there. There are multiple connectivities that are being used. Here you have an example of the Chenonceau brain that allows us to go to 200 micrometer resolution. This is the one that we are actually using routinely nowadays in high resolution brain models. A brain that has been scanned at 11.7 Tesla by Cyril Poupon in Paris at the CEA effectively for a very long time in order to be able to get to this particular resolution, represented both in the human brain atlas, the Jülich brain, and then another one, which is polarized light imaging that allows us, this is spearheaded by Markus Axer and colleagues in Jülich, allows us to obtain actually individual fiber distributions on the level of micrometers. So we are approaching cellular resolution here. When we put this together, and in this example we have done that, where we use an individual brains in vivo obtained from an MRI scan of an individual that we are actually spanning and mapping into the brain reference space, and then link it to the ex vivo Chenonceau connectivity that we are connecting to the same brain template that serves to us as an individual reference. What I will show you later, the in vivo connectivity data, they enter actually then through an inference process where we use the individual in vivo data as a prior to work on the template that is being spanned here by the topographic representation on the one hand side, and the topological, that's the topology that comes from the connectivity. One of the key aspects there that is relevant is actually the, in order to improve the predictive power is when we go into high resolution, you see actually here on the right-hand side that we can, in this resolution, obtain a spatial resolution of 1 millimeter. So we have 2 to 3 square millimeter representation of these triangles you see on the right-hand side. And when this is important when we want to map actually the sources to the individual sensory representations. The way we do this is actually we take the cortical orientation. Subcortical is a little more complicated. I'm not entering into this, but due to the elongations of the individual cells across the different layers, we can actually build individual dipolar moments, put them orthogonal to the cortical surface, and then actually compute the corresponding electric or magnetic fields that come out of this. In the applications of epilepsy, this is actually very important because we have individual context you see represented here in this environment that is actually collecting information from the sources generated to in its voisinage, in its physical proximity. To give you an example, what we do in epilepsy, we use invasive recordings. We enter them into the human's brain. There are individual contexts. And in the current low resolution brains, we are actually performing a sampling that is typically dependent on the distance. So they focus on the yellow contact on this needle, on this electrode. And then it's actually in the low resolution, we have about 400 areas per hemisphere. We are actually sampling the individual areas around that and can actually color code the contribution here distributed here. In the high resolution brain, we can actually take the dipolar orientation into account, which doesn't make any sense at all in the low resolution, because in the low resolution, it has a spatial average area of 10 to 20 square centimeters. Their dipolar orientation doesn't make any sense whatsoever. Here we can do this, and you actually see that we obtain a detailed mapping of the electric field. Through this, we actually inform the source to sensor mapping. That's one element that is actually extremely important when we are dealing with the individual brain imaging data of a patient, the source to sensor mapping. The other element is that we need to bias the parameters in the brain models. This is how we can do this actually. We have different neurotypes, the cytoarchitectures, the different neurotransmitter and receptor distributions as you just discussed. They are represented in an appropriate parcellation, and they are actually providing biases to the parameters in the individual models. The individual models for a brain region, they are obtained from a mean field studies. So these are essentially statistical reductions of dynamic models of individual neurons that have been developed in the HPP over the past 8 years. Yeah, Alain Destex has spearheaded this program. And the interface to the data is always a mathematical parameters in there. These data in the atlas are biasing actually these parameters. And Gustavo Deco has provided a beautiful study cited down here in Science Advantage just 1 or 2 years ago, actually demonstrating that this bias is enormous in order to improve the predictive power of the individual models on an individual level. Once we do this, I show you an example actually what type of modeling we can do. Here is experimental data on 2 scales. This is an electrocorticogram organized on the cortical surface. These are individual contacts. These are empirical data of a single patient. And there where you see the red cross, we have a microelectrode array, which is actually on the millimeter scale. And you see the organization of the data. In the high resolution representation, we can now go into the model, into the individual vertices, and for the hypothesized epileptogenic zone, we can actually increase the parameters linked to the epileptogenicity in these areas and actually start reproducing this type of simulations. Let me go into more detail here. This is a rhinal cortex. Now we are talking models. This is a rhinal cortex in the model space represented. This is a Chenon-Saut connectivity, so the fibers emanating from the rhinal cortex within the hemisphere and crossing the hemisphere. You can quantify this. Here you have a graph theoretical representation of the centrality in this, connectivity strength in this particular case for the rhinal fibers. And we increase the epileptogenicity in these particular areas. And what you see is the following. I'd like to point this out. It's activity, stop. You see activity started emanating here, and then without having to propagate through this intermediate tissue, it starts arising here. This is through the fibers. And And I'll start the simulation again. Look, it propagates, it starts arising here, and only now it starts reorganizing and start recruiting other areas and propagating, generating spiral organizational patterns. This is actually the type of dynamics we can now manage at high resolutions. We can also link across simulators, for instance, a virtual brain and a point neuron simulator, which is NEST in EBRAINS. And this technology referred to as co-simulation, which has been just developed in EBRAINS. And then we can actually choose one area region of interest at high resolution in terms of NEST, so point neurons. And then another one of the rest is provided by the virtual brain using the type of high resolution vertices that I just showed you using mean fields. For the point neuron simulations, we do the following. We go into the atlas. The data have been provided by Javier de Felipe. There are anatomical data available, actually, where he did perform some electron microscopy, allowing to actually identify, extract out of the images 14 million of cells in 3D, their positions. This work done with Michele Migliore and Egidio D'Angela that are representing them for the CA1 region in 3-dimensional physical space. We can reconstruct the individual dendritic and axonal trees and build probability clouds, which allow us to provide a parameterization with the models and actually compute the connection probability and start actually running simulations. And here you see an example. This is just for proof of concept now, a simulation for without embedding into the virtual brain the isolated human CA1 by itself. And here, when it's embedded with all the different connections emanating out of there. So this is an example. Now, what I showed you examples of how we can now use the atlas constraining the parameters of performing simulations. There are other uses also of such individualized, personalized brain models, where they can be actually as a template for fitting. And there we are far enough to go into the clinical applications, where we actually use individual brain images, represent them, extract them from the data set of an individual patient, represent them in the brain reference space, topography, topology, span a three-dimensional network, and equip them with the dynamics we just talked about and all the parameters in there. Sometimes we can refine them through individual information available also for the individual patient. And then we are using them as a template for data fitting, because one of the key questions in epilepsy is where actually is the epileptogenic zone? If you cannot control it through medication, pharmaceutical approaches, and this is the case for 30 to 40% of all epilepsy patients, resective surgery is the only option. And this, the epileptogenic zone needs to be actually outlined in detail. And the consequences are the following. We can actually estimate this using methods from machine learning, Bayesian inference. And here you see actually post-surgical MRI overlaid with the outcome of this estimation using the virtual epileptic patient, it's called, when you perform this workflow. And here it goes actually very well, wonderful over correspondence between the surgery that was performed and actually the estimation. And here you see a very bad correspondence when you look at the surgery that was performed and the estimation. There is a clinical trial using this that is ongoing in France, actually with 13 reference centers all over France, actually using this estimation and taking it into account in the decision-making for 400 patients. This being evaluated at last 4 years, the clinical trial. This is the inclusion rate of the patients. So today, this was December, today we are at around 270. So we are almost there. End of next year, we hope to finish the clinical trial. Some first results for the retrospective patients are represented here. Seizure-free patients, you see actually what is coming out of VEP. The estimation of the epileptogenic zone using this information is actually at least comparable to the clinical hypothesis, the work that is being done, and actually drops significantly for non-seizure-free patients after the surgery. I'm at the end. What I wanted to give you is an impression of what can be done when you link high-resolution brain atlases to mathematical modeling. You can perform simulation. You can actually use it as a template for fitting and can actually build an entire ecosystem in which actually data are coming from the real world, constraining a digital twin of the brain that you then operate in your preferred application, clinical application, and actually sending information back and guiding the surgery or whatever type of diagnostics and treatment you want to do. This is our approach. I'm stopping here at this point. I thank my colleagues, and in particular the clinical team and the funders. And if you have any questions, I'm happy to respond.